All right, I'm going to show you an example of one of these same problems that we do in an area of a curved object, and we're gonna do it using the y-axis as a boundary instead of the x-axis. So far, we've been using the y-axis or the x-axis as a boundary, but we're going to find the area between the y-axis and the curve now. Notice they've given us a function of y, and this is when we're going to use this. They've given us a function where they're just using y's. So if I were to graph this function, f of y equal to y squared, if you plug 0 in for y, you'll get 0 for x. If you plug 1 in for y, you're going to get 1 in for x, because 1 squared is 1. All right, you'll end up getting a curve like this for the graph, okay? And we're going to evaluate, we're going to find the area from 0 to 1, so we can just stop there. So what we're going to do is we are going to find the area of this curve between the x-axis and the y-axis. Or sorry, between the curve and the y-axis like this. We're going to find the area of these, and remember how we do that? We're going to take the limit of the summation. All right, we found out at the very end of the last video that we only really have to do it once. We don't have to find the upper and the lower bound. All right, we only have to do it once if we take the limit of it as n approaches infinity. And this, it doesn't really change much. We're still going to have the same stuff. All right, we're going from 0 to 1. All right, we're still going to take our upper and our lower bound and subtract them and divide them by n to figure out how many our distance, all right, between each of our rectangles. So we're still going to go 1 minus 0 all over n. So our distance between each of these is going to be 1 all over n. All right, we're still going to figure out we're starting at 0 as our endpoint. Plus, well, each of our distance is just going to be I over n. We found out in the last video that since we only have to do one of these, it'd be way easier just to use the I instead of the I minus 1 endpoint. So here's what we're using, our I over n. All right. And then we found out, all right, well, all we need to do to find the area of this is we need to take the limit as n approaches infinity. So what we're doing, we're taking the limit as we choose more and more and more boxes, because we know the more and more boxes that we choose, all right, the closer to the actual area we'll get. All right, so we're taking the limit as n approaches infinity and of the summation. So we're adding up all the areas, I equal to 1 and n. All right, and remember what we did is we took the height right here and take it times the width. Well, to find the height, we already decided that was just going to be 1 over n for each of those rectangles, no matter what. So our height was going to be 1 over n. And to figure out what then its length was to go from here to here, well, we better figure out what this point is on the graph. How do we do that? Well, we plug it into the function. All right, so we're going to say we're going to plug I over n. This is where this comes in handy. I over n squared. We just plug that into the function there. Okay. So we just need to evaluate this now. Remember what we did. We tried to get the i's by itself, pull any n's that we could out so we could use our nice little formulas for I. All right, so let's go ahead. When I bring my square through, I'm going to have I squared, n squared. So when I multiply these two, I'll have n cubed. I can pull a 1 all over n cubed out, and I'll just be left over with an I squared on the inside. So we'll take the limit still as n approaches infinity of 1 all over n cubed, and the summation then, I equal to 1 n of I squared. All right, well, we can look back and we know the formula for I squared. This works out pretty nice for us. So we're going to have the limit as n approaches infinity. If we look back at our formula, the summation of I squared was going to be n times n plus 1 times 2n plus 1 all over 6. All right, well, now all there's left is just to take the limit. And to take the limit, let's just simplify. All right, so let's bring this through and we'll simplify everything. So actually, before we bring that through, we can cross one of these ends out. This could be squared, and this guy can go away. So we're just going to have the limit as n approaches infinity of n plus 1 times 2n plus 1 all over 6n squared. Then all we need to do is FOIL. And so let's have the limit as n approaches infinity, and let's FOIL that thing out. When we FOIL that out, we're going to get 2n squared plus 3n plus 1 all over 6n squared. Well, we can break each of these into their own separate fractions. So here is one fraction. Here's another fraction. So we're going to have 2n squared all over 6n squared, 3n all over 6n squared, and then 1 all over 6n squared. All right, so let's simplify a little bit. So I want the limit as n approaches infinity. I put 2 over n squared over 6 over n squared and be left over with just a 1/3. The n squareds cancel out. We can simplify 2/6 to 1/3. When I put 3n all over 6n squared, the top end cancels out, and actually so does the 3. All right, so we're actually going to end up with 1 all over 2n, and then we'll put 1 all over 6n squared as well. And then we're just taking the limit as n approaches infinity. Well, the first thing we do when we take a limit is we plug it in and see what happens. So let's just plug infinity into here and see what happens. We found out, let's see, was it last chapter or chapter before that? When we have some number all over infinity, we know that number approaches then 0. And this number approaches 0. So the limit as n approaches infinity of this guy right here is going to be just 1/3. So what we just found out is we found the area between this curve and the y-axis here is approximately, or actually is, 1/3. Okay. So there's an example using the y-axis as a boundary, and I hope this helps. We'll see you in class.